This is the TwinAmp Pro, a 2-channel variable output power supply capable of delivering up to 1.5 amps of current at 3 to 14 volts. This power supply features standard banana jacks on all electrical interfaces and convenient slide potentiometers to allow for quick voltage adjustments. Coming in a nifty package with large 7-segment displays and a clear enclosure, the TwinAmp Pro is both easy to use and easy on the eyes. In addition to its looks, this power supply flexes a suite of features such as high-accuracy current and voltage diagnostics and fast-acting resettable electronic fuses so your circuits, and you, receive power safely. The development of this project served as an excellent opportunity to practice skills in schematic capture, PCB layout, system integration, troubleshooting, and of course, teamwork. Most notably, the team is proud to share that almost the entire circuitry of the project sits on 3 unique custom-made PCBs. Stick with me now and find out more about the technical details of the TwinAmp Pro.
The output display is made up of 4 quad 7-segment displays and provides the user feedback on the voltage and current values at each channel's output. Its bright LEDs and amber tint make it easy to see the values even with its very low power consumption. The 7-segment displays utilize a common ground LED array, making it easier to control multiple segments with fewer pins. The display also has a 7-segment decoder ICs, which simplify the 7-segment control to just 4 binary inputs. All combined, the microcontroller is able to control 16 7-segment digits with just 16 output pins. The channels are controlled with slide potentiometers underneath the display that let the user choose which voltage each channel will output. This voltage output goes to the channel connectors that allow the user to use multiple types of connections such as banana plugs or stripped wire to connect to the voltage output. The entire power supply is enclosed with a unique water-jetted front cover and machined clear sides, showing off the electronics while keeping them safe from water and tampering at an IP43 level. The case body was created in CAD software with PCB models inside to ensure everything was mounted properly and fit inside the enclosure.
At the heart of each power supply channel is a buck converter, which consists of a switching MOSFET to reduce or buck the output voltage via pulse width modulation and reactive components to smooth out the chopped up signal. In addition to producing a smoother signal, the reactive components also serve as energy storage to reduce losses in the converter. To achieve both a high level of efficiency and a manageable level of complexity, a Texas Instruments integrated buck converter controller was selected. This TI controller handles the switching and feedback aspects of the buck converter, housing both the MOSFET and the PWM which controls it, while the team takes care of output smoothing. The output voltage of the converter is set by a potentiometer which tunes a reference voltage internal to the buck controller and instructs it to output a particular voltage. The buck controller integrated circuit then interprets the instructions sent by the potentiometer and adjusts the switching frequency of the PWM accordingly to efficiently output the requested voltage. This strategy leaves the fine-tuning of the output voltage to the professionals at Texas Instruments and has enabled our buck implementation to run at a peak efficiency of greater than 90%. To accompany the primary converter, any good variable output power supply must provide diagnostics which inform the user of the voltage and current which is being delivered by the device. To accurately measure these quantities, an integrated circuit which measures voltage, current, and power called a power monitor was implemented. Our power monitor, another Texas Instruments chip, uses a single multiplexed analog to digital converter which measures both the voltage and current of a channel and outputs it to the microcontroller via I2C communication. The operation of the power monitor is quite simple. Upon startup, the microcontroller sends the power monitor a message which specifies the value of the shunt resistor used for current measurement to calibrate the device. Once the power monitor indicates that it has received the message, the microcontroller sends messages specifying whether it would like a voltage or a current value, which is then returned to the microcontroller. In addition to sending a voltage and current over I2C, the power monitor can also send alerts to the master device when the monitor detects a specific current threshold. Though this was not implemented, a future revision of this project could use this alert signal to replace each channel's fuse with a discrete MOSFET. However, as you'll see in the next section, the eFuse fares quite well anyways.
This next block is the overcurrent protection for the system. It has 2 inputs and 2 outputs. The 2 inputs are 2 different channels supplying a voltage. The block then checks to make sure the current does not exceed 1.5 amps. The outputs are the 2 channels outputting that voltage if the current does not exceed 1.5 amps. It does this by using an eFuse. For this block, we wanted to ensure that our interface definitions matched with the data sheet for the eFuse we found. The recommended specifications for this part said that the minimum voltage should be around 2.7 volts and the minimum current should be around 0.125 amps for the part to operate well. We set the maximum voltage as 16 in order to give some leeway between the value and the 14 volts we had to output for the engineering requirement. For the input, no maximum current had to be set since it was internally limited, and the output would have a maximum current of 1.5 amps, since that's when the eFuse would shut off. This schematic was taken from the data sheet for the eFuse as a typical application. From this, we were able to do some calculations to get specific values for each part. Resistors 1 through 3 are voltage dividers meant for setting the under and over voltage lockout set points. RILM was used in order to set the overload current limit for the eFuse. The diodes are there in order to protect the circuit from an inrush of current when the power is suddenly turned on or off. CdVdt and Cout are meant to limit power dissipation, and lastly, Cin is meant to suppress any transients due to inductance from wiring or PCB routing. In order to do all these calculations, we needed to specify a few design parameters. The ones we needed to make were input voltage extremes, the under and over voltage lockout set points, and the current limit. The input voltage and current limit were already mentioned in the interface definitions, and the under and over voltage lockout set points were set to 1.5 and 16 volts respectively. This was chosen for the same reason as VN in order to allow a little leeway on either side of the max and min for the engineering requirement. The next block is firmware. The firmware is an important part of the project as it is what allows us to display values. Our initial plan was to use I2Cs to read the voltage and current, but with problems arising and for an interest of time, we had to scrap the idea and instead use ADCs to read voltage. We programmed the STM32 nuclear board using Cube IDE. In order to work with the output display and the ADCs, we had to assign 18 pins on the nuclear board, 2 input pins for the ADCs, and 16 output pins, which consisted of 2 timer pins, 2 data pins, 4 blank pins, and 8 pins for binary values for the 7-segment decoder. The program is configured with an interrupt timer, which is running at 80 MHz and has a prescaler of 1. Every time the clock resets, the function goes through, incrementing a counter, and initially takes the values from the ADC and scaling them as needed for the output value. Then, each of those values are converted to a string based on the value of the counter. That character is converted to binary and sent to the display. The rest is working with the counter variable. If the counter is equal to 1 or 5, it enables the data pins, which enables the shift registers on the display. When the counter is less than 5, it sets blank 1 pins to high, which turns on the first screen. Otherwise, it turns off blank 1 pins and turns on blank 2 pins, which allows the second screen to be on. And lastly, when the clock reaches 9, it resets, ensuring that the display will loop through the digits.
Thank you for listening to our project showcase video. We had a great time creating this project, and we were super excited to show you all our favorite features, being the buck converter that provided power to all of our inside components and the output channels, our eFuse, which kept our power supply safe from shorts and overcurrent, and our microcontroller, which controlled the entire system. In the future, we plan on integrating a rectifier circuit to our power supply so it can be powered by a common outlet, improving its use by allowing it to be connected to almost any room, powering any need you might have. Thank you.